Greetings to everyone from IIT Kanpur. So let's continue our discussion on ion implantation. We had already seen the first part of the discussion on ion implantation. Today we will dive deeper into actually the profiles that are formed because of the ion implantation. So let's get started. This is ion implantation part 2, the disclaimer. This is the overview about the discussion on ion implantation that we are having. The first part, we talked about ion implantation in the context of VLSI, where it is useful and why we need to learn about it. Then we saw a glimpse of the ion implanter, what is involved in building the ion implanter and how it operates. Today we look at two broad topics, certainly not exhaustive about all about ion implantation, but at least some of the key aspects that it will be helpful for you to know. We will discuss about implant profiles. When you do an implantation, how do you know what is the profile of the concentration you are getting? And this is very important because you want to design your devices according to these profiles in the appropriate way. So if you know what it is, you can design your devices. And then we look at some of the issues that ion implantation faces from the device processing point of view and how people have tried to overcome it. Some of them may not have been completely overcome, but at least you have a way of managing the issues. So let's get started. So we'll discuss about implant profiles. You can get a lot of information in the textbooks that have already been discussed. In fact, all of them, as I mentioned, do talk about aspects of ion implantation into varying degrees. I am mainly emphasizing on what is discussed in Wolf and Tauber in this particular lecture, especially the first session of it. So this is the outline of what I am going to be talking in this section of this lecture. I will be talking about the theory of ion stopping. So when the ion comes crashing in, what are the broad theories, and based on that, how do you model the implant profile? At least we will get an idea and at least the references that you may want to pursue if you are interested in it. So first of all, we want to model how the implantation concentration gets formed when you do the implantation. After that, of course, you have the annealing, which will be similar to what we discussed in diffusion discussion, right? It takes over. So if you look at it, I have tried to present this and I have shared the ideas that are there in Wolf and Tauber with increasing complexity, how this has been modeled. First of all, you assume that the ions are hard spheres and then see when it crashes into a matrix how they interact because of it getting reflected back or deflected or whatever. So that's one way of modeling it, but a more accurate model would be to use the Coulombic interaction, because as the ion comes in, the nuclei are all sitting there and they are all positively charged, right? And this is a positive charge that is coming in. So there is a potential distribution that is present already in the matrix into which the ion is coming and crashing in. So the target atom's potential will interact with the ion that is coming in, and how they interact, and that can be modeled. So this will lead to mainly the nuclear interaction is what we are talking about here. And as it interacts, the energy will be gradually lost and it will be transferred to the target atoms, and that is where the heat will get, it will generate heat and it will slowly get dissipated or get transferred over time. So this is the nucleus that is ending up stopping the ion that is coming into the target. But it is not just the nucleus, you can also have electrons which will end up interacting with the ions. Remember that ion is positive and electrons are negative, so they will also have an interaction and in trying to slow down, and they will also take up the momentum from the ion. Typically, this is more predominant in lighter atoms, and the left nuclear interaction is there in all the heavier atoms and also in the lighter atoms when it becomes much slower. So, a combination of these are at play at any time. When an ion comes in, the nucleus tries to stop, also the electron tries to stop. A combination of that, you look at it, and then interesting theory, simple basics of what we have mentioned, has been developed, LSS, by 3 scientists, and that helps us predict what will be the range of the atom or the ion in the material, and also what the straggle that you are going to get. And based on that, and they assume of course a Gaussian model, it is assumed that it is a random process, and eventually, and they assume that it ends up becoming a Gaussian because of randomness, and they try to model this, and it is essentially a 2 moments model, that is, one is the mean and another is the standard deviation or the variance, whichever one you are wanting to consider. So, this yields Rp, delta Rp, longitudinal straggle, and also the lateral straggle, because it is not just in the direction of the ion that it is coming in that you are going to get a variation in the movement, but also it is going to go on the sides, either left or right, top or bottom, whatever. So, that lateral straggle also has to be considered, and we will see that is important, especially when you are having a mask and you are trying to implant something. It just does not go down, but it goes to the sides underneath the mask as well. So, we need to have a model of that. Why do you need that? Because you need to know what is the difference between a gap you need to place between the openings, so that the devices do not end up interacting due to this lateral straggle. So, that can also be modeled. So, this is the basic thing that is often what we will end up using, especially in the academic world when we start off. But when you want to go for more sophisticated model, this is not enough to capture the full reality. It is valid, of course, it is valid in a small range of concentrations, but when you go for nuances, then you will find that this is not fitting very nicely. So, what do you do? What modelers often, device modelers often do? They invoke more parameters. So, one of the things that they do is go for a third moment. Why keep only 2 moments? Go for a third moment. Third moment ends up being the skew. So, it need not be symmetric. Gaussian is a symmetric distribution. It need not be symmetric, and practically we do see that it is not symmetric. Whatever is lighter atoms will get reflected back more. So, as a result, you will find that the concentration is towards the direction from which it comes. Heavier atoms, on the other hand, may be having a center of gravity or center of first moment on the other side. So, it need not be symmetric. The skew is captured. This can be captured by a couple of ways. You can either invoke skew directly, or you can use 2 Gaussians. There is one for the part that is the initial part and one for the later part, and that is one way of modeling it. And this actually works, it captures quite a bit of the actual profile for amorphous material. But if you want to get a little bit more sophisticated model, you can go for 4th moment as well. The kurtosis, or the 4th moment, also you invoke. So, you have 4 parameters with which you are trying to model it, and this is good for all amorphous material, and the skewness and the kurtosis both are captured. Okay. So, this is what is interesting about using parameters which are of course physical. You know that there is a 4th moment that you are trying to calculate, and with that you are trying to do it. So, this is good, but sometimes there are some special situations, especially when you are implanting, you are not sure that you are necessarily implanting in an amorphous material. You may be implanting in a crystalline material. Crystalline materials will behave little differently. You can have some channels formed. If it gets into a channel, it may keep going through the crystal lattice without having to without being stopped so effectively. So, it ends up going a little deeper. So, all this has to be, if you want to model more correctly, you will have to go for even more sophisticated models. That is, you assume one for the regular implant and one for the channel part. That also you model with a 4 parameter distribution. So, this is another way. So, this ends up Pearson 4 model, which is enhanced with more parameters, that is able to capture the tail that we are talking about, the tail that comes because of the channeling part. So, this is actually pretty good for most applications. That being said, nowadays we are becoming more and more sophisticated and we are going for smaller and smaller devices. So, any variation that you are having is going to be having a big impact on the devices that you are building. So, you have to be extremely careful that you are able to model it very precisely. So, that being the case, sometimes you have to go for the Monte Carlo approach. So, here and also that may not be, we make some assumptions when we are doing the previous models. We are assuming that it is directly implanting into the substrate, but many times there could be other layers that are present before the actual target, the final target where you want the ions to be sitting. So, that being the case, the earlier models may not capture the physics that well. So, best thing would be to go for a Boltzmann transport equation model, and this is first principles, that is every atom you make it follow all the laws of physics, and then you create a randomness in how it is going to encounter that matrix in the target. So, using that, there is the Monte Carlo method. Actually, Monte Carlo is a location where it's a gambling place where lots of these probability ideas were developed. It's interesting that that was the place which ends up providing a lot of fuel for learning about probability and statistics. But anyway, so using that, and actually this is able to capture very realistically in many situations. And in fact, these are extremely sophisticated and there are very good tools that are available, and I'll touch upon them, examples of some tools, and those tools can help you model more effectively, and that way you can quickly at least get a first order understanding what would happen when you implant. Of course, having said all this, finally the proof of the pudding is in the eating. So, you may have an excellent recipe, you may have lots of people telling you and advising you, but you have to actually make the pudding to know whether it tastes well with that particular recipe, right? The same with processing, you actually have to build the device finally and back analyze and then verify. So, but then these models reduce the amount of verification that you will end up having to do eventually, and that is the power of simulations and modeling, which is very critical for the success of VLSI. So, let us move forward and see how they have modeled. Before diving into the details of the model, this is the broad overview which I would want you to know. This is the key part that I want you to know, and the later parts are for those who are more interested can go deeper and learn. And if you are and hopefully these other material that is will be discussed will help you in the learning process. So, let us look at what is essential for you to know as a process engineer. So, typically you have an ion that is coming in that crashes in, and it will crash in normal to the surface. Why is it normal to the surface? This goes back to electrostatics. We know that all fields emanate normal to the surface that you have. So, the ion is actually unless it is suddenly changing direction or something, it's actually coming straight from the along the electrostatic lines, right? Along the field lines. So, so it will end up crashing normal to the surface. But when it comes normal to the surface, once it comes in, it finds that it has way too much energy than the thermal equilibrium will allow, and it ends up colliding with all sorts of other things that are present in the target, mainly the nucleus and the electrons, and those are the two main things that it will encounter. So, once it comes in, it starts losing its normal direction. And there is no guarantee which way it will go. It is a random event. So, it may go up, down, top, bottom, whatever is the two-dimensional thing. So, it will go in any direction. And here, for example, it is shown it is going to the left here or top here, whichever we want to say. It is taking this trajectory, and as it is going, remember, it is crashing with all sorts of other nuclei that are present there. So, as it is going, it is meandering and finding its way, and finally it will end up lose all its energy, and once it loses all its kinetic energy, its velocity becomes 0, it just stays put there. So, it is like something that has come and landed there. So, so you notice that Ri for every ion that is going to come in is going to be different. Every ion will be different. So, but for a given ion there will be a particular Ri, and the projection of it in the direction in which you are wanting to implant, this is the direction you want to implant. So, the projection of that is going to be RPI. So, P stands for projection. So, this is what is of interest to us. Why? Statistically, that is where the average will end up becoming for the all the different ions that are coming. So, the average of that is likely to be the RP. And similarly, this has a particular deviation. So, this is R perpendicular in this for the ith thing will be this much. So, this also has to be collected. This information in the all the directions should be collected. So, the R perpendicular as well as in the longitudinal direction. So, longitudinal direction will be the variation that is happening in this direction. Okay. So, the statistics will bring that out. So, once it is done, you expect, of course, this is a simplification, and you start off with simple models, right. You assume it is a Gaussian. So, if you are plotting this in log scale, it will end up becoming something like this. So, you will find that this is a paraboloid, if I may say so. So, you may find that the peak of the concentration will be at Rp, the average of the thing. Remember, note that the subscript is dropped here because this is representing the average, statistical average, and you will have a variation delta Rp in the direction in which it is coming. It is coming along x here. So, its direction, and also along y and z direction there will be a delta R perpendicular, okay, lateral straggle you may call it. So, so these are the two variables, three variables that we usually talk about: Rp, delta Rp and delta R perpendicular, which is straggle. So, these are the for a given ion you will have a range to which it goes, but the projected range is what is important in term, because it is a planar process, right. From the top you are implanting and you want to know how deep it has gone. That is the projected range of the ion, RPI and R perpendicular. This is there for every ion, but statistically RP will be can be evaluated. If you do this for a large number, you evaluate this, and even analytically when you do, you can come up with these numbers. So, RP statistical average is the first moment, okay. And here I want to bring in a little bit of the physics of it. Note that this RP depends on the implantation, the bias that you are applying for implantation. So, the energy that this ion gains, which will be electronic charge times the number of charge present in the ion, usually it is 1. So, electronic charge times the V implantation. So, that is the kinetic energy that with which it is crashing in, and the Rp that you get for the statistically would be a function of that bias of implantation that you are using. Delta Rp, the straggle, which will be in the longitudinal direction, the direction of the implant, delta Rp, that is a second moment, okay. Second moment, which is, you must have all studied this standard deviation that we talk about. So, second moment, this also will be a function of the bias that you are applying, and the lateral straggle also will be a function of the bias that we are applying. So, this is the statistically derived parameters that we will get. As you might have guessed, the average of the straggle direction deviation should be 0, okay, but the standard deviation will be there because there is a distribution. But average should be 0 because there is no bias that you are applying perpendicular direction. You are applying direction only perpendicular in the direction of the wafer, normal to the wafer surface, but parallel to the wafer surface there are no bias. So, statistically we expect that the average should be equal to 0. Note that the average, so now where is the maximum? Cmax will be at the Rp location, okay. Now, this maximum value that you are going to get will depend on the dose. Dose means how many ions you have put in. The more ions you put in, more will be the obviously the amplitude of the Cmax, but then it is distributed in a statistical way around that Rp. So, now what is this dose value? This we have already seen. D sub implant, what was discussed in the previous thing. So you can say once it has entered, we can call it phi. Okay, entered the material, you can call it phi. Phi will be integral 0 to T implant of the exact ion current using the Faraday cup that we talked about, integrated over time divided by Q. That will be the dose. That is the material you have put inside, and the peak value is in a way proportional to that. And the Cmax therefore is of course a function of ion and the time. The higher the current of implantation and longer you are implanting, your peak concentration will be high. This is all common sense, I would think. Now for dopants, we are not just interested in how much material we have put in. We also want to know where it ends up compensating the other type of dopant. That is what usually you are encountering. Of course, the same type there is no compensation, but if it is, there is another, the background is say P type and you are implanting N type material like phosphorus, you want to know where the concentration that you have put in is going to just compensate and be the background concentration. Beyond that, it will remain the original doping. Before that will be the new dopant that you have put in, new type of material you have put in. So N type, it will become N type, and the rest of it will be P type. So this depends of course on where the junction is formed, and that will be a function of the bias that you are applying, because that determines how much it is spread out, the dose you are putting, because the more material means more it will spread out, and also it depends on ND, where ND is the background doping. Okay, the doping of the substrate, I have put it as ND, so that will be the background. Okay, so this is just for a broad understanding of what are the parameters involved, and this is important. Once you know the basics, rest of it you can always pick up. So why are we looking at this? Because often we are ending up implanting in some region. With respect to the surface, we want to know where how it is distributed. Also, many times it is confined, right? Some implants of course will be for a full wafer, you could do that, but very often it is a masked region. Mask opening is where the implant is taking place. So here, for example, supposing there is a mask which is able to block the implantation, and there is an opening in the mask, through that it is getting implanted. And this is the profile you are likely to get if you take a line parallel to the surface. Okay, so the implantation through the gap is thick mask, and your assumption of course is, often we make this assumption, and this is often true, because as I have already mentioned that lateral dimensions usually are orders of magnitude more than the vertical dimensions, right. So you will find that the opening A is much larger than delta RP and delta R perpendicular, right, and it assumes that and of course X direction, it's assumed that you have full target, same material, much larger than the range of implantation. Sometimes you may find that there could be some other material here, so that will interact, but here it's assumed that it is going very large, and that's often the case in most of the implantation. Now, what is also of interest is what is the contour. So if I go down, this is how the contour will look like. Okay, so what is interesting is this is the edge of the mask. In theory, nothing should get under the mask, right? But what is at the edge? What is happening is, because of the lateral straggle, whatever is getting implanted, some of it is going this way also. Of course, some goes this way, some goes this way and this way. So at the edges, you'll find a lateral straggle. So this is also important to know. So the contours of equal ion concentration is given for a particular case that I picked up from the textbook. 70 kiloelectron volt boron ion is implanted through a 1 micron opening, right? Half a micron and half a micron. This is angstrom that is given, so that's the unit. So RP ends up becoming where the peak is, that is 271 nanometers or 2710 angstrom. Okay, that's where the RP is. Delta RP ends up becoming 824 angstrom. The delta RP is the straggle in the vertical direction, the direction of the implant. But in the lateral direction, the delta RP for boron ends up becoming 1006 angstrom, 100.6 angstrom. Note that for boron and lighter atoms, we often find that the delta lateral straggle is more than the vertical straggle. Okay, So, lateral straggle makes it go under the mask. This is important because you need to know how far away you should make the next mask, so that the two implantations do not end up merging. If they end up merging, you will find that they are all shorted. You often want to isolate the devices, right? So, you have to know the distance. So, this is why lateral straggle is very important, and this is the implant profile. You can determine that. So, now let us go to the theory of the ion stopping. How is the ion being stopped? And a little bit more deeper, at least pointing to the papers that have worked it all out. So, first of all, the rate of energy loss in an ion is what we need to look at, because ion is coming in with a huge amount of kinetic energy, right? It has been, the ion has been accelerated over, say, 10 kilo electron volt, or it could even be 1 mega electron volt. It has been accelerated very much. So, depending on how much bias you are applied, it is accelerating and coming. Now, once it crashes into the target, how does it lose its energy? And that is the key part, because finally when it stops losing its energy, it stays put there. So, it has reached its final destination, and that is where the dopants or the implanted material is going to pile up, implanted ions are going to pile up. So, we need to understand how the dissipation of energy takes place, and the dissipation of energy, we break it into two components. One is dissipation due to the nuclei that is present in the target, or the electrons that are present in the target. So, there are two components, S sub n and S sub e, and one would think common sense that they are functions of the energy with which the ions come in. First order, they will be how much it stops. So, more is the difference, more chance that it will object to this new entity that is coming in with very high energy. Less energy means it may be not so strong in its objection of the new element coming in. And so, once there is an objection, what happens? It scatters it, hits it, and sends it other directions. And in the process, the target atom also gets moved around. So, here Sn are the losses due to this, and they are stopping the ions that are coming in. Now, what is the distance it goes? That can be just found out by integrating the whole thing. And once you integrate it with components x direction, you will be able to how far, what you can the projected region, the projection also you can find out. So, but R is equal to the integral that zero energy loss to losing its energy completely. So, dE divided by dE by dx. And why is it minus? Because it is an energy loss. As energy gets as it keeps moving, energy keeps going down, and that is why it becomes a negative thing. By doing this integration, you will get what is the total range. So, nuclear stopping, let us look at the physics of what is happening. Nuclear stopping can be visualized as collision between two hard spheres, and these are well studied in various contexts. Billiard balls interaction we have studied in our early physics also, but here just that the scale is more. There are lot many target atoms and lot more ions that are coming in. So, you are statistically looking at large numbers, but then that may not be the best way in this particular context, because these are there is a Coulombic effect, right. So, billiard balls assumption is comes and hits and then goes. Many times it may not, even before it comes to some distance, the repulsion force will be very high. So, it will be scattered, or it may be directly deviated even at some distance away, especially if it is at a slow velocity. Even far away from the atom, it may end up nucleus in the atom, it may get deflected. So, it is better to look at scattering by Coulombic force and at a distance interaction. It need not just always come right to that point. And the appropriate atomic scattering V of R can be found out. There are lots of models available, and the popular LSS model use modified Thomas Fermi screening potential, and this is the model that they have used for their evaluation in that paper that they have worked out. Electronic stopping, on the other hand, is a little different. Remember that electrons in all targets will be the same, right. So, the electronic target stopping from the target side will not be dependent on the mass of the atomic nucleuses, right? The atoms that are present in the target. So, electronic stopping, it can be viewed as a projectile in a viscous medium. Okay, and this essentially it can be modeled, and of course there are parameters that come in which will depend on the mass of the ion that is coming in. This ends up becoming Ke times e to the power half. So, what is this? Essentially kinetic energy is half mv square, right? The square root of that is therefore proportional to the velocity that it is having. So, higher the speed, higher will be the stopping effect. So, S of E will be is proportional to the velocity, and that is a constant Ke, and these can also be modeled based using first order physics for analyzing this. So, let us look at these two components, how they are behaving. Here left side graph, you can see the energy with which the ion is coming in. It has been accelerated by 10 kilovolts. So, energy will be 10 kilo electron volts, 100 kilo electrons or 1000 kilo electron volts, 1 mega electron volt, and how much it loses per micron as it goes through that thing. So, if you notice here, the nuclear stopping values are given here, and the electronic stopping values appear as a straight line. So, what it tells is initially it is linearly changing, then there is a maximum amount, and then after that the loss of energy is less and less and less. Okay. So, that is what you find, on the other hand, electronic stopping keeps going up. You also notice another thing, that the lighter atoms, the nuclear stopping is less. Boron is a lighter atom. What we are showing is boron, phosphorus and arsenic has been taken as an example here, and you can see boron nuclear stopping loss of energy is less. Electronic stopping on the other hand is similar for all. So, you find that even for a slightly higher energy of lighter atom implantation, it is the electronic stopping that will dominate. Okay. So, and it goes like this, and on the other hand for heavier atoms, it is a nuclear stopping that dominates. Arsenic is more heavy than phosphorus, you can see even more is higher, and then eventually when they you will find that when you go for very high kinetic energy, that means it is moving with a very fast velocity. Under such situations, if it is such, even the heavier atoms, the nucleus is not able to stop it, because by the time the nucleus potential is going to affect it, it has gone past it. So, that the screening will happen. So, it will be very fast, it will be going. So, as a result, you will find that electronic stopping will dominate if you implant with a very high energy. This is not something very strange. I think analogy I gave you last time, if you throw a stone on a window pane, when it is slow, you find that all glass that is present all around will start interacting with it and will try to slow it down, and in the process the glass will also shatter. On the other hand, if I have a bullet hitting a glass pane, you can see that only in the region where the bullet is hitting the interaction is there, but rest of it is not. Before they can react, the bullet has already gone past, which is why you find that the glass may not shatter when you shoot a bullet, whereas if you throw a stone, it may shatter, because by the time it can react, the thing has gone. So, nuclear stopping is something similar. When you are having a very high energy, by the time the nucleus can get together and stop, especially the ones that are far away, this would have gone. Of course, the nucleus that is directly in its path will of course interact, that there is no doubt about it, but the stopping will be mostly, and because that mass will be comparable to the mass of the single ion, it is not the clump of nuclei that are ending up interacting with the ion that is coming in, it is a fewer nuclei. So, that way nuclear stopping effect will be less. So, this is also shown schematically here with normalized units. This has been plotted. So, you can see that nuclear stopping, it initially increases with the energy of implant, peaks and then comes down. Electronic also goes like this, but in fact in the usual implant range that we are involved in, we do not usually encounter this peaking of the electronic stopping and then coming down. This means that if it is extremely fast, even electrons will not be able to stop, nucleus will be able to stop. Of course, some energy losses will be there a little bit, but it will be negligible compared to the overall energy it has. It will just go through the whole thing. Okay, so that's what we are finding. So let's look at the details a little bit. Nuclear stopping, I have already mentioned, linearly increases, saturates, and then drops with energy. High velocity ions move past target nucleus very fast before they can, there is energy transfer. Heavier ions, arsenic and phosphorus, have higher nuclear stopping. So it has to be at a much higher energy to see that nuclear stopping not playing that much of a role. They are strongly dependent on ion and target atoms. Okay, nuclear stopping will depend on both the ions that are coming in as well as the target. Electronic stopping, on the other hand, is proportional to the velocity, and so square root of kinetic energy, we already saw that, and that's what can be used, and it is used in this particular model. This dominates for lower energy for lighter ions, because boron, you see already it's more than that. But for higher heavier atoms, the electronic stopping will come in only if you are using very high energy implantation, which often is not the case, because we usually go for shallow implants, and becoming shallower and shallower as the device's sizes are shrinking. So this is broad categories of what is playing a role for which type of ions that are getting implanted. Now, when I am at this, before we go dive into the looking at the profiles that you can get, let me also talk about the damage that happens during implantation. And just skimming through this, there is a lot of discussion that can be had in this, because this is important. How it, depending on the damage, you might have to decide how you want to implant, and what you want to implant, and where you want to implant, right? Whether you can repair it or not, all those aspects. So let's look at the damage, how it happens. If you have low dose and in individual small regions, the damages will be in that regions. A very low dose, because very few are actually going in, because remember that they fall off. The number of ions that are going deep will be much smaller compared to where the peak value is. So usually for low dose individual regions, you will have localized damage. So remember that other regions may not be as much damaged. On the other hand, most of them are intermediate dose. You need some dose for except for maybe threshold adjust or something, you may use very little, but typically you need slightly higher 10 to the 13, 10 to the 14 type of dose, so sometimes of course source drain you have very high dose. So light ions, what happens? Remember that they are typically stopped by electrons. That means electrons will not get, because if they are moved away, they can always come back. They are very much mobile, right? Ions, the lattice nucleus, nucleus of the atoms that are present in the target, if they move, that's a damage, correct? So you will find that along the pathway there will be some damage, and most of the damage will take place towards the end, where the velocities are less, and and remember that electronic stopping is less for the with lower velocity, right? Then nuclear stopping will start dominating, and towards the very end, there will always be some damage present. So even in all these branches at the end, you may have some this. Of course, most of the damage will occur where it ends up finally settling down. Remember that when the ion is coming crashing in, sometimes it may knock off some other target nuclei also away from its location, and that becomes a secondary ballistic material that is going through the marine. So all these branch defects that we are saying is because of the secondary acceleration that is caused to the nucleus that have been displaced from their place. So these are all secondary. So primarily most of the damage will be at the end, where closer to where the ion that is implanted comes to rest. The picture is slightly different for heavy ions. Heavy ions primarily are stopped by the nuclei. So that means you will find most of the damage will happen close to the surface itself. Okay? Whereas for lighter atoms, damages could happen deeper inside. This has repercussions in how you design devices, etc. Now, on the other hand, if you have high dose, for any material, any ion that you are implanting, there is a threshold. Beyond that value, the material where it is entering will become amorphized. Heavier ions, obviously, lower a dose itself, you will find that it becomes amorphized. So, high dose, you will have amorphous layer formed right at the surface itself. Typically, a dose of 10 to the power 16 is enough to make the surface amorphous. And that is why if you want to make silicon crystalline surface amorphous, best way would be to implant silicon itself. You are not contaminating it because you are putting silicon in silicon, but if you have a dose of 10 to the power 16 or so, the surface becomes amorphous. Now, you can always have later annealing to have solid state solid phase epitaxy to grow the crystal back by annealing. That is of course possible, but just after the implant there, it will become amorphous, and especially so for heavier ions that are there. Okay, ions of phosphorus, arsenic, and silicon. Now, let us look at the LSS model for implantation in amorphous solids. Remember that LSS model is developed assuming that the surface is amorphous, so that it moves randomly and there are no channeling and so on. Quickly, let us look at what it is trying to tell. This is, of course, LSS stands for Linhart, Scharf, and Schott, right? LSS. So, they are assuming that is implanted in amorphous medium, and as what they have done is the electronic stopping, they have just replaced it by Ke e to the power half, that is, as we saw, proportional to the velocity, and S of n is actually more involved. It brings in. Now, they are try to normalize the units, and independent of what ion is there or what target is there. So, they try to define a normalized distance parameter rho, which is given by this term, which involves the mass of the target as well as the ion. This is the ion, this is the target, and you can see that each component will play a role. This is the area of influence, the screening distance that you have, and this is the range that you are expecting from the ions that are implanted and what dose you are putting in. And this the energy loss, that also is dependent on those parameters and also on the atomic number of the particles. So, M1 and the subscript 1 stands for incident ions and subscript 2 stands for target atoms. Okay, and you can go through that and you can see how the screening distance A is playing a role. And this is where I said that if you have hard balls interaction, you will find that a billiard ball type of interaction, if you take, they have to hit each other. Here, even from far, the Coulombic interaction will take place, and that is where the screening parameter A comes in. Okay. So, when the influence starts, if it is too far away, the nucleus which are far away will not play any role because they are screened by the other nuclei that are present. So, the screen, you have to take that into account because if more are affecting it, the more will be the stopping. So, that is important as well. So, you can actually find out it becomes the atomic number of the ion and the target. So, it assumes that electronic loss is the same as what we discussed earlier, and using the Thomas Fermi screening potential for nuclear energy loss, this leads to Rp, the projected distance given by this. And for those who are interested, the original paper is listed here. It is a very old paper, 1963. Of course, the fundamentals are the same, does not matter if it is old or new, what is true is true. So, this is one simplified approach of analyzing, and it has stood the test of time and it is useful. So, those interested can look up that paper. So, LSS assumes that the implanted distribution will be a symmetric Gaussian because it assumes it is a random process what is happening, and usually you will find that they tend towards a Gaussian distribution. Of course, once you realize that it is not totally random and there are parameters, that brings in the skew and the kurtosis and other things, right. So, this is the distribution that it assumes, and based on that, you can actually find out what the RP will be, which is given in equation 6, and delta RP is given by this term. Okay, this is from first principles. If you analyze, this is what you get. What is the brilliance about this? It's very useful. It may not be very accurate to the nth level, and especially nowadays with smaller and smaller devices, you want very high accuracy, but it's very practical for many simple activities of semiconductor processing that we have to do when we are doing, even when we are doing a complex process. Now, at x equal to RP, we get the maximum to be this. This is based on the Gaussian distribution, which I have already alluded to you earlier in an earlier slide. So, based on this, actually that has been plotted, and there are a couple, original plotting is there, and some people have referred to it in the edited book by Professor Z. Seidel has referred to this. So, if you look at this, this is the projected range that we get for a typical nuclear that are considered as typical ions that are considered as boron ion, phosphorus ion, and arsenic ion, that are usually the dopants that we end up encountering, and this is the straggle that you get for those ions. Now, if you look at it, notice, and here there is the range that is given for silicon and silicon dioxide. Silicon dioxide, of course, is amorphous, and silicon also, you are assuming that there is a thin layer of amorphous on top to make this quite accurate. So, if you look at it, for silicon and silicon dioxide, boron is similar. Why is that? Because it's electronic stopping. Electronic stopping, whether it's silicon or silicon dioxide, it's electrons or electrons. So, it's not playing much, it's not making much of a difference, and you can see it is similar for boron. Whereas phosphorus and arsenic, they are different because it is nuclear stopping. SiO2 will be different, there are oxygen atoms also present, the arrangement is different. So, it will play a role, nuclear stoppings will play a role. So, you find that there is a difference between Si and SiO2. SiO2 actually is able to block the ions more. So, that is why SiO2 can be a good masking layer. Okay? And you also see that, of course, boron gets much further inside because it is a lighter atom, and so it is able to find its way, and it goes deeper, and that is what you get from here. And let us look at the straggle. What do we see? We see that the lateral straggle and the longitudinal straggle is in the direction of the implant. Longitudinal straggle is always more than the lateral straggle, or if not always, more for most of the range of operation that we are interested in for the heavier ions. On the other hand, lighter ion, you find lateral straggle is actually more than the longitudinal straggle. This again has to do with the electronic stopping being the primary mode of stopping. And if you can see, for very high energies, even the phosphorus, it starts becoming similar, because at very high energy we saw that electronic stopping will start taking over because the velocities are very high. So, electronic stopping will start playing a role. Okay. This is a useful plot, and this is available in many of the texts. Almost all the textbooks have reproduced this, and this is something that you often use if you want to do some experiment for your own in the lab, or if you are starting off something in a processing company. Now, as per the LSS, we get a Gaussian distribution, and we have already discussed the concentration will end up becoming this. This is the classic Gaussian equation. So, it is useful to the first order, it is very useful, and it is a good way to start off. If I want to know what it is likely to be, instead of using a lot of resources and very sophisticated software tools, just to do a back of the envelope calculation itself, or simple simulation tools, you can use this LSS model and you can get this. Within 1% accuracy, you can get it for the peaks. So that is pretty good. Within 1% for the peak concentration is pretty good prediction, right? But while the peak values are good, and often the peak value is the depth of implant, but as soon as you come to the straggle and other things, it starts to deviate. So, deviation for low energy is there, and also for shallow implants also you will end up getting the thing. So, significant deviation, you will find that 0.1 of the peak concentration 1/10 of it, remember these are log scales, so 1/10 is the next level. So you will find next decade, so you will find that the deviations start playing a role. So shallow implant, low energy implants, as well as for lower concentrations in the profile, your predictions may not be that accurate. Okay. So we need to consider now, what do? We bring in other parameters, and that's a natural way you should do. It's a more complex process, so you need other parameters to describe that complexity. What are the process complexities that you may get? You may find there is a skew, it is not symmetric. Some of them are piling up early and earlier, and there is a mean value, peak value, and then it starts going down. Peak value, remind you, is not equal to the average, right? Peak value is average only for symmetric distributions, especially like Gaussian. The peak is the same as the mean in this case. So skew of the distribution can play a role, and also the flatness, that is how sharp is the peak and how flat it is. Those will tell you, especially for the tails, you need that. It may be that the peak value you are predicting well, but it's not, it is very sharp, say, then it is dropping off very fast, but your Gaussian says that the value is more. Or if it is very flat, flatter than the Gaussian, your Gaussian says some value, but actually it is higher than that, and then of course it comes down. It's like a table, right? So that is captured by the kurtosis, or the fourth moment. So, but that being, and one of the key things you note here is, this is for amorphous target implantation. In crystalline material, there is a channeling, which we will talk about a little later also, how to overcome the immediately or in the short run, or even to model. This clearly is not capturing the channeling effects. So you have the long tails that you get because of the channeling, this will not be able to capture. So let's see how to improve. We can go for a 3-parameter model. A 3-parameter model, one is to find, of course, the skewness and try to fit it, but a simpler way would be to assume there are two Gaussians. There is a peak value, there is one Gaussian here with a sigma 2 and one Gaussian with a sigma 1. Okay, and this can actually end up telling you what the distribution can be. To at least you will be able to capture some of the deviations that were earlier there for the lower concentration regions, and that's important because that's where the junctions gets defined. Remember that the junctions get defined at very low concentration equal to the background concentration of the dopants, for dopants. So to address the asymmetry in the implant, we can assume that there are two sigmas. Okay, and this is how we do it. And one is valid on this side, another is valid on the other side. Okay, so you have one Gaussian here and one Gaussian here. Of course, the denominator sigma and sigma 2, because that will ensure that the total values that you are finding at the peak location is addressed. So you can see that in this particular case, the RP ends up becoming 0.8 times sigma 2 minus sigma 1. Okay, and delta RP is this, gamma will be given by this. So essentially, you are using one more parameter to try and somehow fit it better. It is okay for heavier ions, but not so good for boron, because boron is lighter, electronic stopping, and there is much more nuances that are coming into play. So here we do need to include one more parameter. So we go for Pearson 4 approximation. So supposing this is the thing, projected range, you take the first moment RP, straggle the second moment or the variance, that or the standard deviation. If you take the square root, you are taking delta RP, not RP square, delta RP, so it's standard deviation. Then the skewness is captured by the third moment. Notice that x minus RP whole cubed times the concentration times dx, that is being integrated. So this is why it is third moment. Of course, finally it should have units of distance, so you will get that. And kurtosis, you will take the fourth moment, x minus RP whole cubed, and saying that's what you are using. So using these statistical tools, you are able to capture this well. and here are the details actually. So for those interested, you can look out. You can define 4 parameters: A, B naught, B1, B2. Okay, hidden in those will be the 4 moments. Okay, this is a practical way of they do it, and this is where you can implement it in the computer. So Pearson 4 model actually captures it quite well, the overall thing, even for boron, and actually this proves it. So here this again is taken from a published paper, and this also reproduced in the textbook Wolfentauber, and also in many other textbooks also you'll find it. So if you take a Gaussian model for 800 kilo electron volt implant, this is going to be looking like this. 300 is looking like this. 100 is looking like this. 30 is like this. But what is the actual distribution? The dots indicate the actual distribution. Now, when you use a 4 moment model, that is a Pearson 4 model, you'll find that it captures it quite well, almost to the full range, except for small deviations at very low concentration, that is 3 orders of concentration less. Earlier, 1 order itself it was deviating, and in some cases even for that it is quite accurate. For 800 kilo electron volt implant, you can see that the 4 parameter model is able to predict very well what your profile is going to be. And so if you increase the dose, everything goes up, everything goes down, you are able to do that. So this is a wonderful way. So lighter atoms undergo more backscattering and is likely to remain near the surface. Heavier atoms, on the other hand, less backscattering, and they pile up after the mean. So this is what you'll end up finding. You find a good fit for 3 moment, but 3 moment model, but 4 moment model is much better. This is not surprising. There is a famous saying of von Neumann. Enrico Fermi quoted him once, that if you give me 4 parameters, I can fit an elephant. Okay, and if you give me a 5th parameter, I can make it wiggle its trunk. Of course, that was a cynical statement, and that often happens when you just go for fitting something with just parameters blindly. But here it's not blind fitting. It's fitting based on some features, where the mean is, what the standard deviation is, what the skew is, and what the kurtosis is. And that comes because of the statistics of scattering as it goes through the medium or the target medium, right? So there is backed by physics. When you implement these, this certainly is a useful model, and it stands the test of time. That's the most important thing. If something changes, if you are just blindly fitting parameters empirically, you have to go through the whole exercise again. Whereas if it's physics based, you'll have to do much less work to again tune to the new environment. Now, channeling in a substrate is an issue. What is this channeling? We'll touch upon this again later in this also, but quickly. You have an incident ion that is coming in. Here it is going in a random way as it was going, but suddenly it finds it's actually is implanted on a plane 763. Actually, what happens is, if you have a crystalline material, if you turn it slightly at a particular thing, it will look like it's as though it's amorphous. Some of you might have joined NCC or Scouts or something. There's a formation of troops that you'll find, and they stand in rows and columns, right? But what is interesting is, if I go to at some angle and look at the whole formation, although they are standing in rows and columns, what you see is a sea of individuals, cadets out there. So if I move in that direction, it will be totally amorphous. On the other hand, if I stand parallel to the row or parallel to the column, I may be able to go through the whole thing without interacting with anybody. So it's the same thing with crystals. In some directions, if you go, it will look like so it is completely amorphous, and that's what they are doing. They are implementing in a direction 763, and what you find is it's behaving like a random thing. But some of the atoms, some of the ions that have come in, after, they of course once they come in they get neutralized, but they are still moving through the material. They are able to find a channel that is 110 direction, and you can see it is just going through. So once it is in a channel, it is not interacting with anything, so it has a smooth passage. So somehow it goes further, and actually this is, you can see this here. When you have at a high energy that is happening, low energy it is not so much, high energy, you find that this is where if it were purely random it should go, but because of this channeling effect, some of them are just getting into the channel, and of course eventually when they slow down, they end up still stopping somewhere. So you'll find that they end up stopping somewhere out here. So you have two peaks. This is because of channeling. This cannot be captured by Pearson 4 model also. So what do? You have to add more parameters. And again, randomly adding parameters is not the point, with some physics. What do? You do one set of parameters for modeling this, one set of parameters for modeling this, and maybe one more parameter to link the two. So that's what is done in the dual Pearson model. You find that you have a concentration and you are actually having one fit here and another fit here, and you are linking them. So 9 parameters are needed in this, and this is useful for modeling the tails. And with this you can pretty much model it with some good accuracies. But then the difficulty is sometimes you need more accuracy. Okay, so let us see what further. They actually use Monte Carlo simulation. This, of course, again the question is how many ions will you model in the implantation. The actual number of ions that are coming is 10 to the power 14 per centimeter square. If you do that number of simulation, then you will take several years or centuries to get that done, or even more, okay, if you want to do it accurately. You actually do only some 1,000 ions or something that are coming in, or 10,000, maybe you may extend it depending on a computer power, maybe 10,000 ions, but it's far less than the actual number of ions. So you have to again know how to do this in a smart way, and based on these, there are quite a few statistical approach is able to simulate the reality. Simulation is scaled down to smaller number of particles. You cannot actually do the actual one, otherwise it's no longer simulation. You are actually repeating the process, right? So simulation is usually a very small fraction of the actual number of particles that are getting implanted, and you use random numbers to simulate the process, but the physics is embedded at the start with each of these ions that are going in. So some software like TRIM, which is very good for amorphous silicon based thing. So if you have amorphized the silicon by implanting silicon, for example, TRIM can be a very good way to predict what is happening for a variety of implant ions. And Marlowe is also very good for crystalline substrates, and there are many other new tools that are constantly coming up, and many of the companies have their own tools which they develop. So they are there. So but they are very good in simulating implanting, and not just for the layers that we talked about. They are especially good when there are multi-layers, which is what is happening. If you look at a FinFET, when you are implanting, you are going to go through many material layers, right? So you have to know what is happening. Multi-layers, and it's able to estimate the recoil of the implant atomic distribution, vacancy distribution, which are also important. It just is not enough to know where your ion has gone. You also need to know where the target atoms have gone. Okay, we have seen that interstitials end up affecting the diffusion. So if you need to know those profiles, so these simulators are pretty powerful in doing that. And nowadays these are routinely used and available. And as I said, every company has its own specialized and proprietary tools for these. So what are the takeaways? The takeaways are the following. Predicting implant profile is important for device design. Is very important. The implanted ion can be stopped by nucleus or by electron. Nuclear stopping, of course, you'd expect it costs more damage. Electronic stopping causes less damage to the lattice, except where it is actually going on its path, and it's more common for lighter atoms. Lighter atom will wiggle around between the atoms, so slightly knocking things a little bit out of its position, but that may come back to its position or may remain in that position, so damage is less. But towards a place where it's going to settle down there, of course, some more damage will be caused. LSS model assumes Gaussian profile and is practical to use, easy to implement, and that's something very good, especially for academic or for training purpose and initial experimental purposes that you are just trying, where the profile need not be so accurate. For those cases, this is very good. but the model is inaccurate when one goes to lower concentrations. So here what you do is you bring in higher moments, and Pearson 4 model captures this very well for amorphous layers, but for dual Pearson model you will find that it's able to capture even for crystalline targets. Monte Carlo simulations are very accurate when simulation is that for simulating implantation profiles, and that's what is increasingly being used today in the industry. Now we come to the next session of our discussion, issues in ion implantation. I'll go over quickly some of the issues that you encounter during the implantation process, and most of it is based on my experience and also from my advisor Professor Nathan Chung's discussions. So this is the outline of what I am going to be talking about. I want to talk about broadly 5 areas in a very brief manner. The channeling of ions during ion implantation. Modeling is one part, but sometimes you don't want it to go deep. You don't want the tails. So what do? You have to come up with some tricks. Another thing is, increasingly we need shallower junctions. Shallow junctions has all sorts of problems. The current of implantation is low, and also the models and the damages are more. So you have to watch out about that. So how do you handle this? And sometimes lighter ions, it's difficult to implant shallow. That's the main issue. Another interesting thing is there is wafer charging during implantation. When implantation takes place, supposing you are an insulator that is getting implanted, as soon as the ion hits it, it gives the charge to the target. Insulator, the charge is just going to sit there. So over time the charge builds up. The insulator may break down. That's an issue. Contamination due to wafer heating. As implantation takes place, the wafer gets heated. When the wafer gets heated, what happens? Some outgassing can take place. Some other reactions can take place. So you have to watch out for those things. Finally, a little bit passing comment. How can we look at alternate implanters? In fact, people have looked at it, and I'll just give one example of that, because implanters can be costly. So channeling, as we have already discussed, when it is arranged in an orderly manner, initially some of them may be random, but some of them can get into a channel. So here you see, if it is in a channel, here it gets knocked again. So it's able to, once in a while getting knocked, it is going through and it will go a much longer distance. That is represented by this cartoon here. Initially it is random, and then once it gets into a channel in crystalline material, it goes through. And people have analyzed how it is going to channel and what are the channeling things in the in our tetrahedral structure or diamond lattice or zinc bend lattice. This is well studied, and you are welcome to look up the details if you are interested. So, but what is the main problem? The junctions are deeper than what we want. So what do? Of course, you should make sure you avoid those channels during the implantation. But how much do we avoid? Can we do something about it? Supposing you have a wafer where the ion that is coming in is bound to directly get into the channel, because remember, it's coming always vertical. So what you do is you tilt the wafer a little bit. You tilt the wafer by around 8 degrees, and that is enough. And depending on the channel, you will know how much to tilt. That is enough to make it appear as though it is random. And once it crashes in, of course, its directions become random. Of course, you still get the tail, but it is much less. Another thing that you can do is, especially when you are doing shallower implant, which we will see later, you can have a screen of amorphous material on top. You can put a thin layer of silicon oxide, for example. SiO2 is amorphous. So when it hits it, the orderly ions that are coming in all parallel, they will go in all random direction. So you are scrambling it. So at least much of the implantation will be in a random manner. So only at the very low implants, low concentrations might end up channeling. Another thing is, you amorphize the silicon. You start off by implanting the silicon with silicon itself, a thin layer, and then you implant. And then of course you can always recrystallize it from the region which is below the range of the implantation, range and few straggles in implantation. that can always recrystallize. This is something that you can always do. So this ensures that there is no channeling and you are able to get it sit in the region that you want. So you amorphize the whole silicon, but make sure of course you are able to eventually recrystallize it from the solid phase epitaxy by the crystalline silicon that is underneath the region which is amorphized. Let's see how you can get low energy implants to get shallow junctions. What is the main problem? Implant with low energy for shallow junctions requires ends up having beam currents because you are using low voltages. The beam currents are less. The beam current is optimum, as we saw, 10 kilovolts to about 100 kilovolts. Less than 10 kilovolts, 5 kilovolts if I am implanting, the beam current is low. So I am not able to get a high dose. It will take a long time to implant. Similarly, if I want to implant something which is more than 1 mega electron volt, that may, and it will take a long time. Of course, there it's going deep. That's not a shallow implant, so that's a different type of problem. Now, when you're having a shallow implant, you're having to go for low energies, that reduces the current. So what do you need to do? You need to be able to implant at a high enough energy, but get the lower dose. Okay, so not lower dose, lower energy for the ion that is getting implanted. You are actually wanting to implant at a higher voltage so that the current is high, but what actually goes in eventually will be slow. So let us see what are the tricks you can use. There are quite a few solutions people have thought of. Implant through a sacrificial layer. Have a buffer layer, so you end up implanting at a higher energy because you need to make sure that the RP will be corresponding to an energy which will be large enough to overcome the buffer layer. But since most of the thing is in the buffer layer, the actual junction that you will get will be shallow when you remove the buffer layer. So you do the implantation, remove the buffer layer. This is one commonsensical solution, correct? So one sleek solution. And of course, what is the buffer layer often used? Oxide. Very easy to grow, very easy to remove also. Another interesting thing that we may not have thought of is to use ion complexes. Okay, polyatomic ions. Okay, so you have a complex of atoms which is coming together and then you ionize it. That is a smart way of doing it. So let's see how to do that. One of the things, before we go into that, a few points I want to mention about this ion implantation. The ions neutralize immediately on their impact. They are charged, but as soon as they come into the thing, then they give the charge to the host, the target. And not just that, if a polyatomic ion complex is coming, it ends up breaking up because the molecule to molecule, atom to atom bond is a few electron volts. The kinetic energy that it has is thousands of electron volt. So in comparison, when it is crashing, all these things go apart. It is similar to maybe when a car hits something at a very high speed, you will find that many of the things that are attached to the car come off because the impact is so much, the overall momentum and kinetic energy of the car is so much, and during the impact all that is ending up dissipating in the various parts of the car. The ones that are attached very lightly, they end up breaking first. The same thing happens here. So atomic binding energies in the molecule is less, energy during impact is huge. So the total momentum is conserved, and what you end up happening is ion complexes will just break up. So the ion complexes implanted at high energy ensures that the current is high because you are using a combination of ions, right? Combination of atoms that is forming an ion. So it's an ion complex. So the mass is high. So you have to use higher energy in order to accelerate it to make it implant. But as soon as it implants, it breaks up into its constituent atoms. So as a result, if only a part of that is the atom that you want to implant, the kinetic energy that will have will be a small fraction of the overall kinetic energy this complex had. So let us take an example and that will become clear. instead of implanting boron atomic mass 11, right? BF2 if I use, fluorine is 19, boron is 11. So if you look at it, the combination should be 49, right, atomic mass units. But as soon as it strikes the thing, only boron has a mass of 11. So the kinetic energy corresponding to that is 11 by 49, right? mv square, velocity of all is same. The change will be very less in the kinetic energy because, as I said, the bond strengths are very low compared to the the kinetic energy that it possesses overall, right? So if I implant with some energy, only 20% of it will be equivalent to implanting boron with 20% of the energy. So you are able to actually implant at a much higher energy. So if I implant say at 10 electron volts, I will end up actually making the boron implant of 2 electron volts, right, 20% of that. So if I make 50, it will be 10 electron volts. So you can find that you are getting a shallower junction, but you are actually implanting at a much higher energy. So this is a very smart way, and in fact people have used all sorts of ion complex. They use diborane B2H6. As you can see here, it is 11 by 28. Some people have been very ambitious, so they have used octadecaborane, so B18, octadeca is 18, B18H22. That means 1/20th of the energy you are imparting to the ion that you is of interest. What happens to hydrogen and fluorine? All they just go away. Okay, and even if they remain, they are benign. They will not play any role. So this is a smart way of tackling the shallow implant question. Now let us look at wafer charging when that can take place. I am shown in schematically. You have a wafer here. The ions are accelerating. You have applied a huge potential. So several kilo electron volts is the kinetic energy that are coming in, and they are crashing in here. So here you have an insulator. As soon as it hits the host, insulator or conductor doesn't matter, it becomes part of the whole system. So the charge becomes part of the whole system. And in an insulator, the charge will just remain there. On the other hand, if it were a conductor, it will just go to the ground. Okay, so or put another way, the electron from ground will come and neutralize that positive ion. So you will have a charge buildup. This is not healthy, especially when you have gate oxides and all that, which can be thin, and you have lots of charge coming there during the implantation, source drain implant and all that. You don't want them to short it. So you have to find ways of dissipating that charge. So ion transfer, over time the insulator can get charged and may cause a breakdown of this insulator. And this insulator that you have may be very critical, like the gate oxide, as I mentioned. So solution is to build an electrical path. So even when you have a poly gate which is getting implanted, you try and make sure that the poly gate is somehow grounded somewhere, if you can. Okay, but one of the other solution is you have an electron shower that is coming in. We saw that it is spinning on a disk, right? So at the time when it is getting implanted, of course it's getting implanted, but as soon as it moves away, electron shower can come in there, and it will neutralize the charge that is built in the oxide. So and that way it compensates for the positive charge that is coming in the insulator. This is one of the tricks that you can use. Of course, you can make sure that your circuit ensures that will be the best. There will be inherent solution. Even if the electron shower doesn't work, it will be possible to use it. So then let's look at the contamination due to wafer heating. Ions implanted transfer kinetic energy to the target, and the target that way gets heated locally. Maybe there is a good heat sink, but locally at the point where it is hitting, some energy is being dissipated. So that ends up heating up locally that region. So photoresist, for example, may get have bonds breaking up because of the impact, or also when they are heated, they may outgas, and that causes contamination. Why? The gases will go out, the ions are hitting the gases, they transfer the momentum to that, the contaminants get implanted. So you are ending up having contamination. Debris might be created by the material on the wafer during implant, and that's not a good idea. What is the solution? You cure the photoresist very well with UV or electron beam stabilization or proper baking in order to harden the photoresist sufficiently so that the outgassing process is reduced. And you can also cover up with a sacrificial thin layer. That's another trick that you can use on top of it, that may, and it may prevent the debris from coming out. If something is flaking off during the implant or it's getting heated and that comes out, if it is capped, that will be prevented. So these are some things that according to the situation you have to work, but these are things you have to watch out for during implantation, because we think that the contamination is less because of the mass selection, but these secondary effects can end up causing contamination, and you should be alert about them. Now finally, let me look at just throw an idea which is been there for quite some time, more than 2.5 decades, looking for a lower cost implanter. The problem is ion implanter we saw is very costly and complex. Can we go for a simpler implanter? One potential solution is plasma immersion ion implantation. Okay, this is something that has been there, as I said, more than 2.5 to 3 decades. So this is the general concept. You have a plasma. Plasma, as we know, is a soup of positive and negative, and usually the positives are ions and negatives are electrons, which are not in thermal equilibrium and going around in that. Now when the target is immersed in that and I apply a bias, what would happen? The ions will get accelerated, come to the sheath, and they'll accelerate through the sheath. The drop in the quasi-neutral region will be negligible. Most of the bias that is applied will be coming across this. This is a very interesting way of doing it, because it can have, it's much simpler setup, right? No scanning, manning and nothing, but at the same time this has its limitations also. So what are the advantages? Very high throughput. What is the limitation? The same limitation that we found in the implanter, the wafer heating up. When so much is getting implanted, it can heat up. So if you have effective cooling, that will limit the how much the throughput that you can have. Another interesting thing that is interesting is the original inventor of this, his point is you have conformal doping. If you have a trench and I want to implant inside the trench, this is a beautiful way of implanting, because the sheath is formed conformally around the trench. Of course, you have to play with the concentration of ions in the plasma, and then when you apply a bias, you get implantation in the trench. This is a wonderful way for doping non-planar structures. This can be of great use, especially when we are going into this non-planar devices like FinFETs and other things. One can try and see whether these can be used. They have their challenges, but this is a potential solution. And of course, the equipment is very simple. It's just a metal body, and inside that you create the plasma and you stick the wafer inside and apply the bias. Often you apply RF bias. You could also use DC implantation. DC implantation has its challenges. It can be a runaway process. So, but at the same time, this is a solution. But what are the disadvantages? No mass separation. So any gas that is coming in can get ionized and get implanted. So the purity aspect that we talked about in ion implantation is sort of compromised. Contaminations of the chamber, all that can come in, because this plasma that is touching the walls, you have to of course protect it with coatings of quartz or something. That's something that will not contaminate your VLSI substrate, but this is certainly more challenging. And of course, plasma uniformity over a large area, it can be done. You can use magnetic fields and other things to get some uniformity. People are using plasma processes for large area substrates, but it can be a challenge to ensure the uniformity that you get, especially with ion implantation, the current existing ion implantation. But all the same, this is I am just leaving you with a novel approach to implantation, and something that you can ponder about. So let's quickly look at the takeaways on issues on ion implantation. There are challenges one encounters during implantation, and many of them have a workaround, and some require more innovations. They may not be the final solution. Channeling is a big issue. tilting the wafer, implanting through amorphous layer, making crystalline silicon amorphous. These are simple tricks. These are why are these being said? These are ideas that people have come up with, and you can often use it in other situations as well. Low energy implants for shallow junction, you can implant through sacrificial layer, so that artificially you make it a high energy implant, so that the currents are high and your throughput is high. But what the wafer is actually seeing is less, because there is a buffer there. Another thing is to implant ion complexes. Wafer charging is an issue, and one way to overcome this is, on insulators you provide an electrical path, either as part of the circuit that you have built, or by some other means during the time of implantation. And also you can make sure that you have electrons being put in it during the off time of the implantation. Contamination is an issue that can come up, especially when you are using some things that are put on the wafer like photoresist. You have to make sure they don't outgas. You have to do whatever is needed to prevent it. If you can, cover up the thing which is going to outgas with some other layer which will not contaminate. And also finally, leaving you with an idea of the cost of the implanter, plasma immersion implantation is a solution. So what is the summary of our discussion on ion implantation? This is a summary. Ion implantation is a key process in today's IC processing. The process helps to keep the thermal budget low. Options to create non-thermodynamically favored structures. This is a very fascinating thing. What you are doing is actually thermodynamically, if you waited for it to happen, it will never happen. Here you are forcing things which are totally non-thermodynamic, and then of course you make sure that it reaches the equilibrium, or at least it doesn't go away from its positions till the lifetime of the device is there. So this opportunity that has opened up is mind-boggling, and so it's a very important aspect of IC VLSI fabrication. Implant profiles have been accurately modeled. Lot of effort has gone in. We also saw in some detail some of the efforts of that. And finally, the process does have challenges, and which process doesn't? Anything which is of value often will have some challenges, but they can be overcome. They have been overcome. But what is more interesting, and especially as academic students and enterprising students, you would want to look at these as opportunities. You can come up with a new solution, and often these solutions can be commonsensical, but in that context they'll have a high value. You can come up with a patent or a unique process and develop intellectual properties. So with that, I'll conclude my discussion on ion implantation. Thank you.